Universidad de Essex en el Reino Unido de Gran Bretaña, y ha trabajado, digamos, en algoritmos evolucionarios utilizados básicamente en inteligencia artificial aplicado a juegos. Esta charla va a hablar sobre algunos temas específicos de la inteligencia artificial aplicada a juegos, y en particular va a estar mostrando algunos aspectos que se están introduciendo en este momento en juegos, en distintos tipos de juegos. O sea, él ha analizado juegos desde los más simples, llamémoslo de los más comunes, ajedrez, Go, etc., hasta mucho más complicados que tienen que ver con videojuegos.
Muchas gracias. Thank you. Okay, we will set a time for 30 minutes. I just think that's immensely cool, the stuff you can do with machine learning. So I understand that for most of you in the audience, maybe it's going to be quite hard to follow me in English. So I will speak quite slowly, and so I can't say as much as I would normally say. And I will show maybe a couple more videos and demonstrations, and maybe I'll pause occasionally to so you can ask questions if you want, and we just see how it goes. And I won't make it last too long, because if you can't understand what I'm saying, it could be quite boring for you. Okay, so that's me. Simon Lucas. I'm the IEEE CIS Vice President for Education. The work I'm talking about is work I've done with these people in my games group plus others. At the moment, I'm at the University of Essex in Colchester, in the UK, and soon I will move to Queen Mary, University of London from August 1st. So, just a quick advert. If any of you fancy doing a PhD, a doctorate in game AI, then we have this wonderful, fully funded program of PhD studentships called the IEEE program. There's the URL. Every year we take about 12 DOTHE students on fully funded studentships. So it's quite very good, I think. So just to put this in some context, this is a very scientific graph. So this is time, and this is the percentage. So AI used to be very restricted, very specific. So you had AI that planned a schedule, maybe that landed an aeroplane, but very specific for the task. Now, over time, it becomes more adaptive, becomes cleverer, becomes more exciting. Okay, you understand? So, this general point is something we can study with games. So, by having an agent play not just one game, but many, many different types of games, it's quite a good test of general intelligence. Now, how can we achieve this general intelligence in AI? Well, for me, the most important things are evolutionary algorithms. So this means rather than specifically program a solution, we just let it evolve over time. Deep learning. You all have heard about deep learning. When I set the timer on my phone just now, the algorithms behind it are deep learning algorithms. They're the best at doing computer vision. They're the best at doing speech recognition. They're the best at doing a whole bunch of different things where you've got lots and lots of data. What you might not have heard so much about, but I'll demonstrate today, is simulation-based learning and planning. This is where we take a model of a system and run it really, really quickly. And we learn in real time, very, very quickly, muy rápido, we learn to behave intelligently. Possible to use hybrids of all three. So you evolve simulation-based AI, which uses deep learning to become smarter over time. Okay. So I've given some motivation for game AI. It's a good test of general AI. The main title of the talk is a new algorithm for noisy optimization. We'll see why that's important. And what we do is adapt a very simple type of evolutionary algorithm. Does anybody have another laser pointer?
Yes, you have.
Got to coordinate two now. Clicker and a pointer. Okay. So the battery's gone on this too. The simplest type of evolutionary algorithm is a random mutation hill climber. We will use that as the starting point, and then we add something clever to make it smarter. Part of the cleverness is called a Bandit algorithm. Has anybody heard of Bandit algorithms? No? Okay, well I'll show you what it involves. Initial results, very good. Okay. Now to appreciate games, why they're a good source of noisy optimization problems, think about the uncertainty that we have in different types of games. For example, you might be playing a card game, like poker. You don't know, you can see your own hands, but you can't see what's in Pablo's hand, or Enrique's hand, or in the deck. There's uncertainty there. You might be playing a game like backgammon. You don't know the outcome of the dice. You might be playing a video game like this, Batman. You don't know the state of the random seed. You don't know what the ghost is going to do next. And any games that have opponents, even a fully observable, fully deterministic game like chess, you can think of the uncertainty of not knowing what your opponent is going to do. So, when we first started doing this, not many people were doing video game AI. But now lots of people are. It's a very, very good thing to do. And we have an IEEE conference sponsored by the Computational Intelligence Society. It's called IEEE CIG, Computational Intelligence in Games. This year it's in New York. Next year it's in Maastricht in the Netherlands. And these are some of the games that we've studied in the past. There's Mario, Talks Car Racing. Can anyone tell me what this game is here?
It's too dark to see it.
Too dark. Any players in the game would be able to recognize it. StarCraft. Yeah. And then this is Miss Pac-Man, that's a real tournament. That's a physical traveling salesman problem. Now, StarCraft is very interesting because for a long time, Go was the big challenge for game AI. Now, I guess you've all heard of AlphaGo, developed by DeepMind. So we now have computers that can play Go at superhuman levels. So AlphaGo now is better than the best Go players in the world. And yet StarCraft remains a challenge for the moment. The best computer players play at the level of like an amateur human player. Better than a novice, but not as good as an expert. So very interesting. Now, what we've done with these games, we've run competitions on many of these. We've run competitions on Pac-Man, Mario, Unreal Tournament, Talks, all of these things. And the methods that we use in our society, we use things like fuzzy systems. Bernadette spoke of fuzzy systems earlier. Talks car racing on 2 different years has been won by fuzzy controllers. Okay? So fuzzy is good for this. Things like Ms. Pac-Man, we have various types of computational intelligence winning this. We have different types of computational intelligence designed by researchers that have won specific competitions. But it does not address the generality. So, for example, if you take one of the controllers that won the Talks competition and you say, okay, car racing bot, now go and play Pac-Man, it hasn't got a clue. It has no idea. Whereas if you take a person and once they get good at one sort of video game, they tend to be also quite good at learning other video games. Now, this is what we study in general video game AI. So it simulates the idea. The challenge for the AI is to play any video game. You don't know what the rules are. You just know the score, and you know when you die. It's cast as a reinforcement learning problem. So it's a bit like walking into the arcade a long time ago and playing a new game like Space Invaders. So that's the challenge. Now, how can we start solving it? This is the website. We run competitions, and there are cash prizes for some of these in conjunction with our conferences. So have a look at that if you're interested. gbgai.net, and the competition sponsored by the IEEE CIS and also by Google DeepMind. There are some videos online that I won't have time to show at the moment. I'm now going to talk about the motivation a bit for the title of the talk. So this is revolving around the why we need bandits. So what we're trying to do in our game AI is one of 2 things. Okay? We're trying to get clever AI to play a game well. So this is real-time control. And for this, we evolve using something called rolling horizon evolution. I'll explain what this is in a minute. The other thing we do is we try to evolve or tune game parameters or rules or content such as level designs to make better games. Okay? So 2 distinct aspects of evolution. We're trying to make smart AI that learns and adapts very, very quickly. And we're also trying to make better games by tuning those games in specific ways, automatically. So, these fitness evaluations are expensive. And they're also noisy. So the noise I mentioned before arises in a number of ways. So, because of the computational expense and the need for speed, we need special algorithms that are very efficient and very robust to noise. Now, Hands up who's heard of an evolutionary algorithm? Not any of you. They're very, very cool. They're very good and very simple in their essence. So this is the algorithm. Of course, it's why we're so sort of complex and wonderful today. We've evolved over millions of years. The algorithm is simple. So you initialize a random population of individuals. You then repeat, you evaluate them, rank them by fitness, and then you breed offspring from the fittest parents. And you do this until you're satisfied or you run out of time. Now, this bit is noisy. When you do the evaluations are subject to noise, so that you have to be careful. Does anybody have another laser pointer, by the way? If not, it doesn't matter. If you do, this is the out there. Okay, so, next one. I just want to demonstrate the operation of one of these algorithms. Okay, so what you see here is a simple evolutionary process. This is code running live, and every time it's picking a square at random and either flipping the state of it. Now, the fittest possible configuration is when it's all yellow, todo amarillo, okay? But what we have to do, the algorithm doesn't know that. It's just making changes at random, and if it leads to an improvement in fitness, it will tend to accept it, and if not, it will tend to reject it. That's the basis of very powerful evolutionary algorithms. You make random changes, you accept them if they seem to be better, you reject them if they seem to be worse. And eventually it converges on a solution. I don't think so. Okay. So that was the demo. Now, what we do, in each case, we're going to use evolution to evolve vectors of integers. We'll use exactly the same algorithms. The only difference is sometimes there will be controlling an agent, other times they'll be optimizing a game design. So for a game, we might be optimizing these type of things, the location of the pills in Pac-Man, missile velocity, jump height in Mario, and so on. So all these things can have quite a big impact on the quality of the game. Now, for the rolling horizon evolution, this is an important, very simple way to develop a game agent. So the idea is that all we need to do is evolve a sequence of actions. So here I've got Pac-Man. Have you all played Pac-Man? You all know what it is? Yeah? Okay, good. When I was about, 16, 15, Pac-Man had just come out, and I was really addicted to it. It was fantastic. So I used to take all my money, just put it in the machine and play. Brilliant fun. So how do we do it with evolution? Well, what we do, in this case, the Pac-Man's here, and one possible route it might take would be to go up, then across, then down. This is coded just as a sequence of integers, so 1 means up, 4 means left, 3 means down, and 2 means right. So that means going like that. So the actions can be repeated a number of times. And you can see this is going to be noisy because actually we don't know what the ghosts are going to do. But we can just say, let's pretend to behave at random. For example, that's one thing we can do. And then I might evaluate the sequence many times, and sometimes I get eaten by the brood ghost, which goes up and eats me, and other times it might turn down there, and this is a perfectly reasonable thing to do. So we make lots of evaluations of these vectors of integers, and each time we can get different results. That's where the noise comes from. And it's called rolling horizon because every time we take an action, we take the first one off this vector, we shift everything along, put a random element in the end, and repeat the process. Now, game design is also noisy. So if we think about adjusting a game, we then have to make some measure of it. Well, we can do that by making agents play the game, and we measure aspects of their experience. But different agents can play the same game in different ways, and so we get a source of noise there. We get a different statistics of the results. So this leads to the core part of the talk, which is about the landscape modelling. So how can we make the most? How can we squeeze as much possible information out of every single fitness measurement we make? So we're trying to learn as much as we can about the problem. So this is your overall system design. In the middle we have an algorithm that's doing the optimization. Every time we make a fitness evaluation, we measure how good something is. We can get a different result, and we always put this into the landscape model. Now, where does the Bandit come in? Well, bandits are used to try to maximize the reward from a system, trying to get as much utility as you can. And it's called a bandit because it's a bit like an octopus playing multiple slot machines in an arcade. And every time it pulls one, it may or may not win. The idea is that some of these machines, they're better than others. They have a more likely probability to win. And it has to learn this over time by observing the results. Now there's an equation behind this. In fact, there are many, many possible equations. This is one of the most popular. It's called UCB for upper confidence bounds. Mu-C is the mean of a particular option. This term here is, so this is the exploitation term. This is high if the options seem to be good. This is the exploration term, and this is high if you've not explored anything yet. So NC is the number of times you've explored a particular option. So to begin with, NC is 0, and so the exploration is infinite, and so you try to explore everything once. Okay. And then this is just a nice way to balance this exploitation versus the exploration. So now you can think of it like a new game, designing these search spaces of possible games and then trying to find interesting points within them. So this is an example game that's been automatically designed, and I'll show you a couple of videos of this a bit later. And the idea is we're tuning things like the missile fire rate. So how frequently can you fire missiles? That affects the nature of the game. And so what we do, we just set up a set of parameters of the game, things like the radius of the missile, the cost of firing one, the cost of being hit by one, and so on. And then we can optimize those things automatically. What we do with the landscape model, every time we make a fitness evaluation, we put data into the model, and then when we search, we use the model to estimate the quality of things. I won't go into the details of this. Now this, I might spend a bit of time just going through this one, because I think it's an interesting slide. This is the core of the optimization algorithm. So you can see it's quite simple. And let's see what it involves. So first of all, a solution is simply a vector. So in Java, it's an array of int. Yeah. What this means is from the search space, pick a random point. Now, while the number of evaluations is less than the total, what I then do is say to the evaluator, evaluate that point and call it the fitness. I take that fitness and I add it to the landscape model and I say, okay, point P, on this occasion, add this fitness. I can take that same point P and evaluate it again and get a very different number for the fitness. But over time, you build up the statistics in this. Then I make a choice evaluator, and I've got this idea of searching the neighborhood via a mutation operator. Then I've got a mutator function, and the mutations can be small, or they can be quite big. Yeah? And then what I do is I keep adding those, evaluating them, and then I pick what appears to be the best one. When all this loop is finished, I then ask the Bandit landscape to get me the best solution that it can find. So in doing it this way, by using the model, over time we build up the statistics of the search space, and we're able to do things much more efficiently than if we didn't have a model. So what we're doing here is now testing it on a sample test problem. So what we're doing here now, we're modeling this, we've got a binary number x, and we're trying to evolve it so that all the ones, all the bits of the number are 1, and the probability of a win is that math.round is less than x over 2 to the n plus 1. So the probability of the win is highest when x is its maximum, and it just starts with a random number. So this is a very noisy function. Every time it's always returning 1 or 0, and it's very noisy to optimize. And this is a simulation of the type of optimization we might be doing for a game. Now, how does this do compared? This now compares the efficiency of using the landscape model, which is up here. This is a Bandit landscape EA, and this one here is the original random mutation hill climber. Now, to overcome the noise, you have to do something called resampling. So this is a resampling rate, and that peaks at about 4 or 5 resamples for fitness evaluation. Now, I've got a very tight budget here. I've only got 100 possible evaluations I'm allowed to make, and you can see that we end up with much, much better results when we do it that way. Okay, so we're going to look now at how this applies to a real world, not a real world game, sorry, an actual simple game. And although we like to tackle more complicated games sometimes, and within our community we do all kinds of games, but this simple space battle game has been designed to provide just a little test challenge. And the objective is the blue ship is trying to get the green ship within its blue disk. And whenever it's in this damage radius, the blue one's going to gain points, and vice versa with the green one. So they're trying to fight around each other to get the other one in the damage disk. Okay? So it's like a stupidly simple game, but it's a nice little test bed. Then just to give another example, I might show a video in a minute of space battle that's also been involved. So we're doing two things. We're involving these actual game designs, and we're also involving the game actions for a game player. Okay, let's have a look at the code. I don't know why the Mac does this, but when I switch over the presentation, it just takes of seconds to switch. Okay, let's see. Okay, so this is going horribly wrong though, right? So the blue one scores on the left, and the green one's on the right. And what you can see, that black kind of messy line, these are these random players. So do you remember in Pac-Man we had that like random sequence of integers? All those black lines, all these lines, and the agent using this model of the game to predict what will happen if it takes a certain sequence of actions. Now, actually, that was up there. So the blue one is the one that's got the rolling horizon evolution in it. The green one's another type of algorithm called Monte Carlo tree search. And it's just an example of fighting these two against each other. Actually, this time, that's not meant to happen. So on this occasion, the green agent won, and that's actually quite a rare result. So we'll just run the game again. And just look out for the way that those playouts, those black lines, happen in different ways. So it's imagining possible futures, and it's when it's got the green one in its sights, they tend to play out in different ways because that tends to be the fittest set of results. And you see again towards the end, it's the blue one's got the green one in its sight, and the players converge to being more focused on tracking the green one because it gets into a more sort of stable state. I think it was just maybe one other video I can show you. This is a space battle game that we evolved in our group. So what we do, we have like a design space of possible games. These are games that have black holes in them, and the agents can get trapped in these. They have pickups where it can pick up more missiles, and then it shot them all too quickly. But at the same time, then we're using these rapidly adaptive AI agents to evolve games, and we evolve the games by measuring the kind of experience that the AI agents have when they play them. And that was quite a good evolved one, I think. This is a less evolved one. So in this game, you can get high scores just by flying around randomly and firing a lot. So that's a game that does not have very much skill. Okay. Oh, right, this is right. Okay, so in summary, it's my last slide. Games really, they provide a fantastic application area for AI or for computational intelligence. You can use, also they give a wonderful source of noisy optimization problems. You can use them for generating smart players. So the players you saw playing those games, they've not been programmed to play any game in particular. They're just using very, very general type of AI that just learns to play any game within a quite a wide class instantly. And you can use this same algorithm also for tuning new games. So the basis of the algorithm, the Bandit landscape EA, is to then use this landscape to build a model of the search space that allows you to search it then much more efficiently. And there's more detail if you go to my webpage. We've just published some papers on this in IEEE CIS 2017. And I'll stop there. I hope you understood a little bit of what I said, at least anyway. Okay, thank you.
I don't know if someone has any questions.